Okay, welcome to the Winds and Currents webinar. This is the last in the scheduled series. We've been working up towards the submission of the Odyssey proposal, and the proposal is due at the beginning of August. After that, the interest in the topics won't go away, but I think we'll want to, as a community, find a slightly different way to organize things so that we continue to bring forward the ideas that are really most important to people. So we'll welcome input on that, but that's a topic for later. Today we have Anthony Kirincich. I realize I don't know how you say your last name, but
very good. Kirincich, sorry.
And who's going to talk about horizontal stirring over the Northeast U.S. continental shelf, eddies, lateral exchange, and eddy kinetic energy at the surface. So take it away.
Thank you, Sarah. Thanks so much. There's a little bit of pressure being the last talk in the series, but I'll try to do that. I'm a coastal oceanographer by training, and so I'm a little bit new to the satellite community on thinking about these larger scales. But I wanted to talk today about some work that I've been doing over the continental shelf, looking at horizontal stirring and perhaps some similar methods as folks are using further offshore, you with the altimeter or some of the other satellite products that are available. And so I wanted to show these recent results that we've seen over the shelf for maybe a new way in the coastal ocean for looking at eddy kinetic energy and wave number spectra using some of the methods that have come out of the satellite community. So again, I'm going to do a lot of this using high frequency radars, which are land-based distributed sensing networks. And I'll talk a little bit about those, but there'll probably be extra questions for folks that might want to learn about the systems later on. Okay, so this is work that I've done with folks here at WHOI, Ben Hodges, and then across UH at Pierre Flamont and Victoria Fulch, who's at the Coast Guard Academy now, as well as Brian Emery and Lyle Washburn from UCSB. Contributed here. So this work is motivated, let me go back to here, by understanding the role of small scales on exchange across the shelf. You know, my interest as a coastal oceanographer is understanding transport across the coastal ocean, whether it's upwelling and downwelling or lateral stirring due to bathymetric features or turbulence, right? And about the same time that I started looking at radar observations as a way to understand the small scales, one of my colleagues, Steve Lentz, mined the current meter and hydrographic record from the Mid-Atlantic Bight, which is what you can see here in this figure from his 2008 paper, to look at all the along shelf flow observations of the Mid-Atlantic Bight and the wind observations, and try to understand what's the interannual mean, or the mean annual balances of heat and salt across the shelf in the Mid-Atlantic Bight. And what his work, to summarize a couple of his papers here, showed was that balances of heat and salt required an eddy flux that was coming in from the open ocean or across the shelf, and that eddy component of the flux was not depth dependent, more likely to be barotropic, but really poorly constrained by observations. And so that kind of motivated some of the work that I did after that to look at some of these smaller scale eddy features. So I spent a couple of years working to identify eddies in high resolution, high frequency radar fields. So these are maps of, this is a map of surface currents sensed by land-based systems, so that all the arrows are vectors of north and east velocity. And I used similar techniques as those by Dudley Chelton and Michael Schlacks and others after that to look at the eddies that are present by defining an eddy as some sort of coherent feature, whether it's in a stream function or an Akuba-Weiss parameter, and then looking at the movement of that eddy structure over time. And it didn't matter the resolution of the radar we used, whether it was really, really high, 400-meter resolution for coastal systems, or more coarse, 1 kilometer resolution or 2 kilometer resolution systems. You found lots of eddies as you get to the resolution of the radar system. And so this plot at the lower left here is the eddy length scale, or like the radius of the eddy that were found. And as you get towards the resolution of the radar system or your observational system, you just get, there's more and more eddies as you get to smaller and smaller scales. The eddies that we found at smaller scales were not eddies in the warm core ring sense, where it's a very trapped core of fluid that is transporting water large different distances relative and long times relative to the rotation scale of the time scale of the eddy, but really short ephemeral features. Especially that was true as you got towards these smaller scale features, where most of the eddies were quite small. Most of the eddies didn't last very long. Here's the eddies that we found in this particular smaller array, where most of them last less than 10 hours. And most of them don't really rotate all the way around. So it's not a warm core ring type eddy. It's a kind of it's a piece of horizontal stirring, right? Or horizontal turbulence. But these all were defined by this definition of an eddy or a coherent structure. And if you kind of back away from that subjective definition of an eddy to look at just stirring, you could do that using by recasting the velocity fields that we got as to try to understand horizontal eddy diffusivity via either a mixing length approach or an eddy kinetic energy approach, following a paper by Ken Brink and Hyode Seo. We saw that the eddy diffusivity, which is kappa here, it was highly variable over time, and so this is about 6 months of radar observations of surface currents, and so for every timestamp of the data, we're getting some estimate of the spatially averaged eddy diffusivity, and they're highly variable in time. 50%, almost 100% differences over time. There's a seasonal difference between summertime periods where the waters are more stratified and wintertime periods, but there's methodological differences too. So these are two different estimates: one mixing length estimate and this timescale estimate following Ken's work. And those themselves are orders of magnitude different in terms of the value of the eddy diffusivity that you had. Each of these were more than what the canonical diffusivity with scale that you would get by going back to Okubo's. This is a diagram from Okubo's paper in 1972. And so our estimates of eddy diffusivity on the scales of like 10 kilometers were up to an order of magnitude more than this kind of canonical stirring, right? And mixing length estimates that we've gotten directly from the radar, they were quite similar to some drifter and radar and dye studies that I did over a couple of years with Arina Rapina, where we used both of the radars and the drifter to match up with the dye and to see what was happening at the sub-radar scales. And these estimates of higher diffusivities in Okubo, I think, match up with some of the work that the Carthay group in working at the Gulf of Mexico have been able to find more recently than this. And so the point of giving this background is to look at, I've kind of evolved from looking at exchange from evolving dynamics, eddy structures, and to thinking more carefully about horizontal stirring of how features and properties can go across the shell. And to kind of summarize, I guess, a little bit of the background, I want to steal a thunder from the end part of the work and show you the result of some of the data that I've collected and I'm going to talk about in an aggregate scale using the wave number spectra. So this is a plot of surface currents. So all the arrows are on a 2 kilometer grid. It's one snapshot. It's a half-hour snapshot of surface currents from radar systems. The radars are all these red dots around the coastline. And you can see a pretty complex pattern. This is a day in August 9th, 2019. So the vectors are ocean currents. This vector right here is about 25 centimeters per second for reference. The color underneath it is a co-located snapshot of AVHRR sea surface temperature. And the thing, the horizontal scale here, to be clear, is about 150 kilometers on the x-axis here, the horizontal between Nantucket and Martha's Vineyard. So this is the northern end of the Mid-Atlantic Bight. And then it's about 90 miles vertically, 90 kilometers vertically up and down here, just for reference. The scale of temperature that you're seeing is over about 10 degrees of surface temperature changes. And what I want to, I guess, point out is in the context of horizontal stirring and exchange, there's a tidal mixing front that exists here over Nantucket Shoals that's been around, and we've known, there's been a lot of work studying that. And there's a front that exists because of that tidal mixing front or the tidal mixing area. And you can see right here about 2 grid points of radar along the 40-meter isobath. So there's about 4 kilometers spacing here between these 3 vectors. and the change in temperature is about 10 degrees. So it's about a 5 degree Celsius change every radar grid point or 2 kilometers. And for reference, the bathymetry here again is 20 and then 40 meters and then the 60-meter isobath. So this is fairly shallow, obviously relative to the open ocean. But this, I'm going to call this a fairly strong gradient in surface temperature. It is much, much weaker by the time the flow field gets to the western side of this domain. And so the flows are moving at about 20 centimeters per second. So that's 5 to 7 days to transit this area. And we drop from that 5 degree over 2 kilometer scale of frontal features to almost the opposite, the inverse of that. So this is about 1 degree every 10 kilometers, I believe, if I got that right. And so the point I'm trying to make with this figure here is there's a lot of structure happening in the coastal ocean. There's a lot of stirring that is occurring over this area that I'm going to look at. And the breakdown of this cross frontal feature over this fairly short coastal zone indicates a lot of stirring across the shelf. And so the point is that the snapshot of horizontal currents and surface temperatures show this dramatic breakdown of horizontal gradients over these fairly short features. And the goal of the work that I want to present today was to analyze these data from the standpoint of the wave number spectra to understand what processes are driving the eddy kinetic energy of the shelf and how they might vary over time, seasonally, and over shorter time periods. And then if we can derive the implications for stirring and exchange. And so I'm going to talk a little bit about the data in a minute, but I first want to kind of preview wave number spectra and the idea of thinking about the ocean from the point of view of wave number spectra. Some of you might know more about this than I do, but the goal of what I'm going to do is to use eddy kinetic energy wave number spectra to examine horizontal stirring. And so there's a couple of plots I'm going to show here for examples of where folks have done this previously in the literature, both observationally and with models. And then I'm going to get into kind of a theoretical basis of what I think I'd like to try to use the spectra for here. Wave number spectra in the ocean, I think, is fairly hard to do. You need a lot of data, and getting spatially dense realizations of velocity and lots of realizations of that can be challenging. I think folks have obviously done this with altimetry at larger scales, but for measurements of velocity in situ, certainly at depth or even at the surface, can be more challenging. This is a figure from Cesar Roca's paper in 2016 of a long and a cross-track wave number spectra from crossings of icebreakers on the Drake Passage. And so you see for both the along and the cross-track spectra, the decay of energy with wave number is almost k to the -2. So this is a representative line of k to the -2, and then there's a higher slope line k to the -3 here. And there were, in Cesar's work here, there was a fairly small differences between the along track and a cross track, and kind of breaking up the flow field into rotational and divergent periods, although there is some at larger scales. Another much smaller in terms of spatial scale estimate of wave number spectra at the surface ocean only came from some work that Sung-Young Kim had been working on over a number of years. This is a particular data set off the South Korean coast. This box right here is about 40 by 40 kilometers, I believe. And he looked at 1 kilometer resolution data sets to look at the kind of the cross shelf and kind of a long shelf, in a sense, view of the ocean using wave number spectra. And so again, this is a smaller scale view of the coastal ocean using radars. I can talk about the challenges of using radars for these estimates, but the point that I wanted to make from their estimates here are he had a couple different ways of plotting this, whether it was in X and Y or using some other method, summer or winter. So the S is for summer and the W is for winter here. There was a characteristic shape that he had where at lower frequencies or lower wave numbers, excuse me, it was matching kind of a 5 to k to the -5/3 slope. And then as you increase the wave number, got to higher wave numbers, it kind of rolled off to something greater than that, whether it was k to the 2 to k to the minus 3, excuse me. It depends on where you kind of were. And so the spectral shape there was of interest to the results that they showed. Okay. The last kind of in situ or observational example is another work by Sung-Young Kim earlier, a little bit earlier, but it was based along the West Coast. And in this work, he merged both altimetry products in a long shelf versions of a long shelf and a long shelf product along the US West Coast with a bunch of different resolutions of high frequency radar using the national network of high frequency radar that exists along the US West Coast. And you can see the black and gray line are altimetry products. There's a space where it is increasing in energy, and then somewhere between 500 and 200 kilometer scales, it decreases as a k to the minus 1. You have this increase here, which I've reading this paper and others is because of the noise of the altimetry system itself. And then at smaller spatial scales than that, or higher wave numbers, you can see the radar products continue to decrease, and there's some variance in where they get to a k to the minus 2 or k to the minus 5/3, and it might depend on kind of the product that you have. And there's some, I'm going to argue that there's some interest here between the slopes of these lines at smaller wave numbers with some of the model results of kinetic energy wave number spectral shape that Xavier Capet and co-authors did in 2008 in this series of papers. And this is one of the figures from their the first paper here, where as you increase the model resolution, the roll-off or the shape of the wave number spectra for surface velocities changed, and this roll-off here, the authors said, was due to model resolution issues, not necessarily dynamical issues. And so there's a couple of interesting points here to make, and what I want to do to close out this motivation is to talk about some of the theoretical work on wave number spectra, and a good paper here from Jorn Calais and Raf Ferrari, where they plotted or did a number of theoretical models to examine the spectral shape at the surface and at depth of a cross track and a long track, as well as buoyancy. And the main conclusion for this work and a number of others that are in the same kind of genre here is that the kinetic energy spectral shape has the potential to reveal the processes and the dynamics that are driving the horizontal motions. And so different dynamical processes might have different kinetic energy shapes. And so if you had a diagnostic property of the spectral shape that was happening, you could look at and see make an inference on what the dynamics that were present. And this paper by Calais and Ferrari and a number of others have talked about balance flows, whether geostrophic or quasi-geostrophic, surface quasi-geostrophic flows, and internal wave scales and other unbalanced flows. And one of a figure here from, or a table from Sung-Young Kim and Son's paper in 2018 kind of shows a nice table that was useful for me for thinking about what the inverse cascade and the forward cascade might look like in terms of its spectral shape based on the type of dynamics that was driving it. And so I think some of you are certainly more of an expert than I am at wave number spectra and spectral fluxes, which I'll talk about later on. But for the analysis that I was looking at here in the coastal ocean using radar observations, the main kind of hypotheses moving forward and looking at the data were, again, the spectral shape can reveal something about the processes and the energies present. The slope can suggest the process. Changes in slope can suggest a change in the process, whether it's due to methods or the model or an actual change in the dynamics. That's an open question that we can look at. And then the overall energy level that could be important for model representation. Say you want to understand if your coastal model system was accurately getting the types and scales of eddies present, looking at the the eddy kinetic energy related to what observationally might be present. It might be an interesting way to do that. Okay, so I took a look at the horizontal stirring. I'm going to call this in the submesoscale. This is not a dynamical definition of submesoscale. What I'm going to say, if I slip and say submesoscale here, I'm really just saying 2 to 20 kilometers of scales. Submesoscale as a dynamic scale would be less than the Rossby radius, which would be in the summertime, a few kilometers, if that. And so I'm really thinking about these scales of 2 to 20 kilometers. And the reason why I'm motivated to do that is if an analysis of the along isobath wave number spectra from SST observations. So I showed that one plot of SST observations from the Mid-Atlantic Bight. This is the northern part again. Here's a couple of snapshots of SSTs from AVHR. This is Cape Cod, Martha's Vineyard, Nantucket, and you see these little temperature filaments that exist. I showed you previously one of those in the plot of combined radar and surface SSTs that I was looking at. If you aggregate all these together, all the cloud-free images that fall into a long isobath range of the radar system that I'm going to talk about, and look at the spectral density or the wave number spectra of this scalar, you can see there's a pretty significant difference between stratified periods, which I'm going to here for the purpose of plotting is June to September, which is the blue line, and then more weekly stratified periods, which I'll justify later on, which is October to December. And I've chosen October to December just based on the availability of cloud-free images. So again, the black lines of our representative slopes for K to -3 and K to -2. You see that the summertime surface temperature variance at all scales is higher in energy than the wintertime. So the blue line is above the red line. The blue line here in the summer follows a K to -2 until you get to somewhere around 20 kilometers, and then it tends to roll over here. And so in the mean, it changes slope from K to -2 to K to -3. In the wintertime, it's a little bit more constant with slope through this space and has, again, lower energy. And so this was work that motivated the analysis of the same time periods using the same methodologies from the surface currents to see if these types of dynamical slopes were present and what if we could come at the drivers of use those slopes to look at the drivers of the dynamics present. And so the flows of this spatial scales I think are critical to the spatially variable exchange and dispersion. That goes back to the drifter studies that we had done previously in this area and work that's been done in the Gulf of Mexico since then, as well as that initial paper by Steve Lentz that was thinking about the eddy fluxes are really important for understanding closing the heat and salt balances for the shelf. Okay, so I'm going to pause for a minute talking about wave number spectra and talking about radar. I obviously think this is a satellite crowd, so you know a lot about satellite methods. Radars are a distributed network. We functionally do the same thing. We're Bragg scattering off of the ocean surface, just at longer wavelengths than satellite products. We're also using grazing angles, so our signals propagate over the horizon and coupling to the sea surface and come back to us. But to do this really well at small scales, like approaching a few kilometers of the few kilometer scale of the SSTs that are available, we actually need to change the way we observe radar systems or the ocean using radar systems. And the reason for that is, I guess like most sensors, a satellite sensor here, the coastal radar systems don't measure in X and Y or Cartesian coordinates, they measure in range and azimuth. So it's a polar estimate, right? The range resolution is set by the FCC. That's the bandwidth that we're allowed to send out. And so we don't really have any method to go, mechanisms to go to greater resolutions than that. But the part that we can do something about is the azimuthal resolution. And it turns out that the azimuthal resolution of a radar is actually the limiting factor to getting high resolution results. The standard, the dominant radar that's commercially available is the CSON by the Kodar Ocean Sensors. This is a picture of one of the CSON antennas right here. It's a single mast with a dome with 3 antennas located inside of this. It uses direction finding to get direction. So it uses the amplitude differences between these 3 antennas to measure where the signal came from. And that's really the crux of the issue here, because the direction finding using a Kodar system is pretty coarse in azimuth, and it can hide and mask small scale features that we want to find. And so I'm going to argue that to do higher resolution studies further away from the coast, we need to do really a better job in measuring azimuth. And so what we've done over the past few years working with myself and Pierre Flamant from the University of Hawaii is to kind of create a generic phased array system that we would run not like a beamforming phased array radar, but more like a direction finding radar. So instead of having 3 antennas, we have 8. They're in a clump. Here's a picture of one of them where it's all poles that are sitting in amongst a coastal dune. I think folks can potentially imagine that the biggest impact or barrier to installing more radar systems, other than the cost of the actual unit, is getting land and to put them in that are useful in the coastal zone. So changing the way we run the radar to be high resolution is, I think, is an important thing for us to try to work on to do these high resolution studies. So I've been using 8-channel direction finding because it can increase the number of emitters that I can find. This is a technical term in the signal processing community. A CSON is limited to 2 emitters for any one velocity it's looking for in any one range. The systems that I'm running really do well up to 4 or even 5 emitters. And so we can get a much richer data set of currents in the area offshore using these systems that have essentially just more antennas. It's not new technology, it's a new implementation of older technology, I guess. And so the last justification for why we've done a little bit different on the increasing the horizontal resolution of the radars is you can look at the theoretical bearing resolution limit of a 3-channel system versus an 8-channel system. And a lot of this is governed by the signal to noise ratio on how well you can do. And what this plot shows you is basically the resolution limit of 2 signals that are the same velocity and how close they can be together, and your radar can tell that there's 2 signals and not 1 signal. So for an SNR of about 20, the uniform rectangular array of 8 channels, the signals can be 10 degrees apart, and you can realize that there are 2 signals there. Whereas for a 3-channel system, it would have to be 30 degrees apart to realize that there's 2 signals there. And so those 2 10-degree spaced signals would be merged into one, and you wouldn't see that richness in the coastal field. So this matters, and the dominant way to see that it matters is to go out and measure velocity at a certain point in space or from a drifter and compare the quality of the surface currents you get from the radar systems against that validation standard, some sort of in situ observations, a drifter or a point sensor in the ocean. And you can see that the RMS difference in just uncertainty is if for this particular data set was 25% less, so between 10 centimeters per second to about 7 centimeters per second, using the different technique of doing the extra horizontal resolution. So the main reason why I think radar is important here relative to satellites, I know this is a satellite crowd, and so this might not be a useful thing to say, is the coastal ocean changes so rapidly. For measuring velocities, we really need to have observations every half an hour or less. And so that's that's the barrier here, I think, for really resolving coastal flows with larger scale products. And so there's my interest in the radar as a observational tool comes from that time scale that we need to resolve. Okay, so there's a couple papers that there's a JTech paper from 2018 that kind of summarizes the methodology here of increasing the resolution. But the main result is that I have a data set that I'm going to use to look at wave number spectra from. It spans this 150 kilometer by about 90 kilometer domain of south of us here at Woods Hole out of convenience. And so this is the island of Nantucket and Block Island. New York is to the left and Boston is to up above here. There are 3 field periods that I'm going to look at the data from. It's basically 2 summers and 3 winters, starting in 2018, 19, and 20. I had a number of moorings in the middle of the radar domain to give me some vertical structure of the currents and the hydrography. And then I had 2 wave gliders, the SV2 models, that were transiting across this butterfly pattern to collect horizontal measurements of temperature and salinity to make sure that I could compare those back to the SST estimates that I showed earlier. And so I'm boiling down a lot of data into a few number of plots to show you. And so hopefully this will make sense. But I think the main important point here is there's 2 summers and 3 winters, and we had some in situ observations. The in situ observations, here's the vertical structure of the surface and bottom temperatures for all years, and then the actual more detail in one particular year. And my main takeaway for you here is starting in July, going to December on the US East Coast, we are well stratified here with a surface mix layer around or shallower than 10 meters in about 40 meters of water. And then over the course of the fall, we mix up and then start to cool. And so there's a winter period where we have very weak stratification. And then there's a summer period where we have much stronger stratification. And so I'm going to bound this kind of 2 months in the summer where there's stronger stratification, and then this winter weaker stratification period, and just look at them a little bit differently here. The wave gliders allow us to look at the time dependence of the structure across the shelf a little bit, as well as compare the in situ data with what I showed earlier from the satellite SSTs. And so here's a couple of time stacks of the across shelf, the along shelf, which is this line, and the across shelf here in red, which is this cross shelf line here, of temperature over about a 30-kilometer transect line with the wave gliders. And we occupied these like twice a day, more or less. And you can take this data and look at the wave number spectra of these scalars. And what you'll see are shown here. So this is the along shelf in the top panel, and the across shelf wave number spectra of temperature in red, and then salinity in blue. And these were all during the stratified periods, so the summer to into the early fall. And you can see that the important point to take away here is the spectral slope is similar in both years. There's a difference in the energy level between the years, but not, and that's much more notable than the change in slope. The slopes that you see for both temperature and salinity again is blue, are much strongerly related to the K⁻3, which is what you saw in the satellite AVHR data at sub 20 kilometers during the summertime. And so I think the takeaway for me here was that the AVHR was temperature only. We have temperature and salinity here, so we have a good handle that the density structure is also decaying at that same K⁻³ structure throughout the entire span, from about 20 or 15 kilometers here down to very small scales, and smaller than what the radar is observing. So to preface going into the wave number spectra results, I wanted to show, this is a plot of wind speed from July all the way through December. So the summer period into the winter period for 1 year. I think this is 2019. They're somewhat similar in this in decay, or in kind of the structure of the observations a little bit. And the point here is that just to break up the mean kinetic energy, which is the spatially averaged kinetic energy, right, is the blue line, and that is throughout summer and winter is very highly correlated with the wind speed. So the surface currents generally follow the wind, and the winds are much larger scale, and so you have these larger scale winds here, and the mean kinetic energy is following the wind pretty closely. The eddy kinetic energy, which I'll define here as the difference from the spatial mean at each time, is more variable. And then in the summertime, it's uncorrelated with the wind forcing. But as you get into the unstratified periods, it actually gets a little bit more weakly correlated with the wind. And so this is just a kind of a hint of what we are going to see, I think, later on with the wave number spectra. Okay, so I looked at the wave number spectra not along the 2D grid that I showed you earlier with that snapshot, but here is another snapshot of all the radial data from all the sites that contributed into this. And I'm going to look at the wave number spectra along isobath and across isobath. And so these lines that are curving through the domain follow the 40-meter isobath plus or minus 5 or 2 meters in isobath. And so at each of these blue dots, I'm estimating the along track and cross track velocity from all the radials that are within a range of that. And I've been really careful about the range that I'm sampling here to make sure I'm keeping the resolution as tight as possible. So the along shelf lines here are pretty straightforward. A cross shelf gets a little bit more complicated because the shelf that I'm like the long shelf line is varying in its XY extent. And so I've broken up the cross shelf into a number of lines that are orthogonal to the long shelf lines, but have a different orientation relative to each other in the east component, and then the central component here, and then a cross shelf in the west, which is closer here over to the Block Island, and this is Rhode Island Sound. And you'll see some of these differences between the west and east sides be a little bit more predominant. So at each of these blue dots, I'm estimating a long track and a cross track velocities directly from the radial observations for every instant in time. I'm taking spectral estimates of them over the entire length, or as long as length as there's no gaps. If there's gaps, that entire record goes out. And over the 3 seasons, field periods, theirs can be up to 15,000 estimates of spectra from these. So if you're looking at the long shelf line, which is this line again, following about the 40-meter isobath, there's this plot kind of orients you to the main results. The k⁻⁵ line is shown here with the k-1. 4 kilometers is my Nyquist wave number because I'm gridding to a 2-kilometer resolution radar. And you have a couple of plots here. There's 2 summers in red and 3 winters of results. And so this is the long shelf wave number spectra over the longest a long shelf line possible, and relative to a noise spectrum, where I've taken that 7 centimeters per second estimate of the uncertainty of the radar, and I've done pseudo spectrum with them to estimate, following the same methods as the radar, as the data themselves, to estimate a noise floor for the calculation. And so the confidence interval is shown below here. So the main conclusion from the long shelf eddy kinetic energy wave number spectra plots, so again, this is 15,000 instances averaged together into 5 or 6 plots here, is generally, at high wave number, the shape of the spectrum is fairly straight, very close to a k⁻⁵. The summer wave number spectra in terms of the energy and the roll-off are very similar, with very small differences between the red dashed line and the red solid line for the 2 summer periods. The 3 winter periods are much more different than the summer periods. At large scale, winters have less energy than the summers do. But at the small scales, the rate of decay, or the slope of the line, is still about the same. So I don't notice any change in the slope between this data in short of 20 kilometers in scale. The only real change in slope that's notable is this in winter 2020, where there is a change from kind of this one lower energy state into this other one. And that's kind of an interesting feature that could be related to the data, but I'm not quite certain about this. But the main takeaway, I think, looking at this estimate is that there's interannual variability in the energy level present between winter and summer. There's no real change in the slope, certainly not at high wave numbers between winter and summer, despite a really significant breakdown in the stratification present between them. If you then divide up the cross-shelf lines into those 3 regions, so the east, the center, and then the west. So here's the east, the center, and the west. The scales are smaller and at the largest scale because the lines are shorter. The results are a little bit more nuanced here, but have the same connotation as what I showed earlier. So again, there can be up to 5 lines here, 2 summers and 3 winters in blue. And you see that at high wave numbers, the slopes in the center and the west are very much k⁻⁵. At low wave numbers, they might roll off to something less than that. But there's very few differences at high wave numbers. There seems to be more of a difference in the overall energy level during that particular season, moving the overall variance up and down rather than changing the slope. And the most differences that we see across the summers and winters come from the eastern line, where the energy levels are actually can be highly variable between winter 19, which is a particularly weak wind winter, and the other winters, which were more normal in terms of their wind forcing. And so the The major difference between the across shelf lines here are in the western part at low wave numbers. You had these decreased energy levels, which indicate some sort of change in slope, I think. And then you don't really see this in the center and in the east. There are some variations at this kind of 30 to 15 or 10 kilometer range, but they're a little bit harder to tease apart what's happening. Okay, so looking at the time, I'm going to skip this plot real fast and go to the final part here, which is the kinetic energy fluxes. I didn't say this earlier, but I did this along and across isobath. You could do this in a Cartesian north-south, east-west grid, and you would get some results that are similar in terms of the spectral slope, but the energy levels would be different because you're co-mingling a long shelf and a cross shelf dynamics here a little bit. But I also did this calculation for the kinetic energy fluxes. And I think folks here know much more about this than I. The reason that I'm interested in the kinetic energy fluxes is that it can tell us a little bit about where energy is moving. And so this is a characteristic figure here from Brian Arabich's 2013 paper. And my takeaway here for the figure is when the kinetic energy fluxes are greater than 0, you have energy moving from that scale to smaller scales. When the kinetic energy fluxes are less than 0 or negative, the energy at that scale is moving to larger scales. And so the location of this zero crossing tells us something about the differentiation point between scales moving to higher, energy moving to higher scales, or energy moving to lower scales. And so using the data set, I estimated the spectral fluxes following the Scott and Wang's method and Brian Arabich's work as well. To look at try to understand the direction of energy transfer here over the seasonal scale. So here's that plot again from Brian Arabich, just to orient yourself to the plot I'm showing. This figure is the monthly average kinetic energy fluxes in the Eastern domain for all years. And the first thing to say is that there's a lot of noise happening at very high wave numbers. But at lower wave numbers, you see a little bit more interesting patterns here of during July, which is the blue line. It is decidedly negative at low wave numbers, and it increases to be positive and significantly positive with increasing wave number here, and this zero crossing is around 18 to 20 kilometers. And so at higher wave numbers, it's a bit hard to tell that this is significantly different from 0. So I'm going to focus on what's happening down here. And as you go from July to August to October to November and December, you can see that area of large positive becomes much smaller, and it becomes more, large negative becomes much smaller and becomes more positive. And so my interpretation of the data here is that in July, in the summer, we're in a regime where the radar observations, which are fixed in their spatial extent, are able to resolve both this area of large scales, transfer of energy from that scale to larger scales, as well as some hint of the energy transfer to smaller scales. As you move into the weekly or unstratified periods, you can see that the point of transition between negative and positive spectral fluxes gets larger than the domain that we're sampling. And so all of the data from the winter are in this area where we're only seeing the energy transfer to small scales. And so in winter, we are just observing the energy transfer to small scales, but in summer, we see that there's the transition scale is present, and we're seeing that potential cutoff between fluxes to large scales and fluxes to smaller scale. And if you bear with me for a minute here, we can take the spectral flux estimates and not just look at them monthly, but look at them over the scales of events. And so using like a 2, I think, or a 3-day smoothing window to look at the spectral fluxes over over all of the data present. And so this is in the eastern domain again. So this is the wave number on the vertical here, and then time is on the horizontal. So the top panel is the data from 2018, the middle is 2019, the bottom is 2020. I don't know why it says Arabic right there. It should be up here back to this plot. Sorry, Brian. But this is that kind of orientation plot here, where you see the energy to small scales is in red or positive, and energy to large scales is in blue or negative. And you can see the time dependence of that transition point between blue and red, or negative and positive, as it varies over the course of the summer, and then into winter, where the data that are significantly different from zero statistically are becoming much more positive, or not significantly different from zero. And you see the same thing happening in the summer period of 2008 or 19 as well. And then 2020 here is a much shorter record here. But again, most of the times we're capturing significant energy levels for kinetic energy fluxes. It's at these larger scales, and we see that transition. Okay, so to summarize, I looked at coastal ocean surface kinetic energy spectra, and I've looked at it's varies seasonally and regionally, due, I think, to potentially changes in stratification and wind forcing. I mentioned that the eddy kinetic energy was more related to the wind in the winter than it is in the summer, and also some bathymetric changes. The difference from the west to east of the cross-shelf lines are likely driven by bathymetry at the longest scales possible there. There is little seasonal variations in the slope of the eddy kinetic energy, and that was a surprising result from when I started into this. And thus it seemed like the stratification that was present, the amount of stratification, and the two-layer dynamics were not really a significant driver of the spectral slope. And I think that and while the area average eddy kinetic energy was unrelated to wind forcing in the summertime, anomalies to the eddy kinetic energy wave number spectrum, certainly in the winter, but also if you look at the anomalies to this plot over the course of smaller time scales, which I didn't actually show here, appear to be wind driven. And so even in the summertime, there is a relationship between the shape of the eddy kinetic energy spectrum and the wind on those shorter time scales. It's a little more difficult to tease out. But the one thing I wanted to end with here on my last slide is methods really matter for this data, and I'm sure this is preaching to the choir here. Getting eddy kinetic energy wave number spectra at sub 10 kilometers is really challenging to do with radars, because it's the azimuthal resolution that matters so much. And so I think there's I should have a little example here of if you over the sample the data differently and you have a different smoothing characteristic, you can kind of create some structure in here that isn't in the result that I had. And so it's a challenging calculation to make. And I think that making it having the spectral fluxes, or sorry, the energy spectrum being constant with decay all the way to the Nyquist wave number here, I think is a significant result, and it's the methods really matter to getting that significant result. The final point here is the event scale variability and fluxes are interesting, and I think they show some promise as a tool to understand the scales present, as well as being able to compare to models. And that's kind of the next step for us, is to try to understand how these results might compare to folks' high resolution models of the area. So I'll stop there.
Thank you very much. This was great. A really great way to wrap up this series. Questions? And maybe while people are thinking, I'll ask about the really challenging aspect of this, getting to super small scales that you brought up. Because I think you've pointed out that when you go to smaller scales, you keep seeing smaller and smaller eddies at the edge of your domain. So that must lead to a lot of worry about what's an eddy and what's noise and how to separate them. I'm wondering how you've navigated that.
I guess I navigated that by stopping looking at eddies as coherent features with kind of an arbitrary definition or a subjective definition of what an eddy was. The eddies, almost all the eddies that I've looked at using radar observations, and I think other folks that have done radar-based eddies have seen this, they're not eddies in the sense of a warm core ring where it's a trapped core fluid that's moving from here to there and rotating, many times, right? They're little bits of stirring where it might rotate once or even less than once over its lifespan. So you have this little whirl that is captured by your technique that exists for an ephemeral amount of time, right? And then kind of disappears. And it has a notable impact on mixing across the shelf because that little bit of stirring actually matters, and you can add up all those little bits of stirring that you might capture from eddies, either the coherently or kind of an incoherent, like a EOF type approach, and see that there's a significant amounts of exchange happening. But I think in this type of analysis, looking at the smallest scales where it's really horizontal stirring or horizontal turbulence, using the definition of like an eddy that's like a trapped, warm, a closed streamline or some sort of a other definition for an eddy, it breaks down.
Thanks. I see that Andre Sherbina has his hand up.
Yeah, Anthony, thanks so much. Cool results. I have two questions. One is that most of your spectra plots show k to the -5/3 and very few k to the -2. I may have missed the justification for that. So is there a reason to believe that -5/3 would be relevant here?
You're asking why didn't I put the black, kind of a example of k to the -2 spectrum on? Is that right? Okay.
Yeah, because based on our sub-mesoscale understanding, it should be -2.
Okay. I guess I arbitrarily picked to compare it to a 5/3 rather than a 6/3. And I could have easily plotted a black a k to the -6/3 or 2 on here as well. So I guess the reading of the literature that I went moving into this was that it was hard and observationally to tell the difference between the two. I know dynamically and theoretically there's a big difference, right? But in terms of observationally, that it seems like some of the work by Cesar and others, it's a little harder to see that. So I could be wrong there, but I guess you're right in saying that I chose an arbitrary line to compare against, and I could have easily and should have chose k to the -2.
Yeah, I can totally relate. It's difficult, but it's just it would be good to see the difference from some predicted value, right? Not some arbitrary value, but it doesn't matter really. Thank you. The other question I had is that with respect to your spectral energy fluxes plot, obviously a lot of that depends on statistical significance, as you said. Could you maybe say a couple of words how you calculate the errors on those fluxes? You had the,
right.
the shading there.
Right. So the errors on the spectral fluxes were based on it was an error propagation from the noise floor of the radar at that scale. And so I propagated that estimate through the calculation to get an estimate of the bounds of that. And I'm not describing that very well right now, but the time dependent KE fluxes that I showed, I've masked out everything that's less than kind of a canonical error bound of like the mean value there. So I think that answers your question a little bit. I used the error estimate I had from the drifter to radar and the velocity to radar comparisons and propagated that through.
Yeah, I'm just surprised that it's very symmetric because the distribution of this third moment is very non-Gaussian. So I would expect the error bars to be very much non-symmetrical.
Okay, that's something for me to
anyway, we can touch base offline. Thanks again.
Yeah. Thank you, Andre.
Great. Eric DeSaro has his hand up. Eric, do you want to go ahead?
I was muted. Ta-da! Okay, hello again.
Hi.
Yeah, that's nice data. That's really nice data, nice methods. Two questions. First of all, did you try doing space-time spectra? There's a lot more information about dynamics in space-time spectra than there would be in spatial spectra alone. That should be really pretty powerful way to do it. So that would be worth trying. you should see dispersion relationships, you should see waves, you should see all sorts of good stuff. Second question is, most of your dynamical comparisons are with open ocean dynamics. The big difference here, particularly in the winter, is you've got bottom friction, and I would think that would do quite a bit to the spectra, and also lead to cross scale the energy exchanges, because whether the large scale currents are big and small controls the damping of the small scale currents if it's a square drag law. So that would be worth, I'm sure someone must have done that somewhere in terms of theory. I think that would affect the interpretation.
Yeah, thanks. Sorry, I was making some notes. Thank you, Eric. I did not do space-time spectra. I wrote that down here, something to look at. So thanks for that suggestion. The comparisons are more open ocean because I don't think folks have done this at over the shelf where there's significant bathymetry. I think that Sung-Young Kim's work on the West Coast for the larger scale radar system was probably well, even that is mostly further offshore than the shelf break, right? And so I was really surprised at over a shallow shelf that the wave number spectral slope was functionally the same between winter and summer. And
It
so I
might be
think that
for a different reason.
that's a good point. Yeah, yeah. So I don't know of any other folks that have done similar estimates over the shelf, but I could be wrong. But thank you.
Thanks.
Great. Tony Lee has his hand up.
Really quick, thank you very much for your talk. I have a question about the spectral level in summer versus winter. It looks like consistently that the red one in the summer is higher than that for winter, which is blue. Is that correct interpretation?
That is correct.
So do you have any thought about why that might be the case?
That's a good question. In this particular plot that I'm showing here on the summary is the places that the red line, the summer, is bigger than the blue line are at these longer spatial scales. So from 50 kilometers or the longest scales down to about 10 kilometers. And I think the interesting part here, I guess, is based on this data, there's not a difference between summer and winter at high wave number, but it's at the lower wave number that you see more energy in summer than winter. My interpretation is that's where the stratification is mattering or matters to drive larger features in the surface flows, right? So there is a mixed layer depth here, about 10 meters in the summertime, and so you might have those structures that you saw on temperature plots that I showed of these whirls and jets and stuff that exist. And I think that's where the energy is coming from, and it's not there in the wintertime. So I think that's where stratification is driving something differently.
Thank you.
Thanks. That's really interesting. I'm glad Tony asked that, because it's something we've been thinking a lot about as we write this proposal. So if you have published results, we're going to be really interested in that.
Thank you.
We are at the end of the hour, and so I want to be aware of people's time. We'll wrap up here. I'm going to stop recording,